Improper integrals. Let's consider the area under the curve of the function y equals 1 over x squared from x equals 1 to x equals some unknown value t. We know to get the area under the curve, we have to take the definite integral from the lower limit of 1 to the upper limit of t of our function 1 over x squared dx. Now, we can evaluate this integral. This is going to be the integral of x to the negative 2 dx from 1 to t. Taking the antiderivative, we get x to the negative 2 plus 1 over negative 2 plus 1. And this is negative 1 over x from 1 to t. When we plug in t, we get negative 1 over t minus, and then when we plug in 1, we get negative 1 over 1. And if we simplify this, we're going to have negative 1 over t plus 1, which is the same as 1 minus 1 over t. Okay, so what this means is that now if we prescribe a value to t, we could simply plug in that value of t and we would get the area under the curve. So for example, if I wanted the area from x equals 1 to x equals 10, we know that the area would be the integral from 1 to 10 of 1 over x squared dx. But we know what this is going to be because we've already calculated this integral up here. So all I need to do is plug in the limit of 10 in for t. And so this would end up being 1 minus 1 over 10, which is 9 over 10. What if I wanted the area from x equals 1 to x equals 100? Well, again, that area would simply be the integral from 1 to 100 of 1 over x squared dx. And now we're just going to substitute t equals 100 into the formula 1 minus 1 over t. And that's going to give us 1 minus 1 100th, which is 99 over 100. And so naturally the question becomes, can we find the area from 1 to infinity? Well, that area would be the integral from 1 to infinity of 1 over x squared dx. And if you think about it, this would be the limit as t goes to infinity of the expression 1 minus 1 over t, right? I mean, that makes sense because, again, we know the area from 1 to any value of t is 1 minus 1 over t. So we can't actually plug in infinity here, but we can take the limit as t goes to infinity. And of course, we know that as t goes to infinity, this value gets smaller and smaller and smaller, and it goes to 0. And so this would become 1 minus 0, which is equal to 1. And so when we have an integral that has an infinite limit, we can define the integral to simply be the limit as that value of t approaches infinity, or I should say as the value of t gets larger. And that is in fact what we're going to do. And so I'll just summarize that here. If I want the area from 1 to infinity, we would take the integral from 1 to infinity of our function. We're going to define this as the limit as t goes to infinity of the integral from 1 to t. Now again, we know that this integral here is 1 minus 1 over t, according to our previous work. And now as we let t go to infinity, this answer comes up to be 1. Now, as you can imagine, when you're finding the area under the curve up to infinity, this limit is not always going to exist and be equal to a number. Sometimes the limit may be infinite. So let's go ahead and do a formal definition here, and then we'll do some problems. So here we have the definition of an improper integral of type 1. Type 1 means that there is an infinity or a negative infinity somewhere in the limits of integration. To integrate from a constant a up to positive infinity, we take the limit as t goes to infinity, and then we integrate from a to t. To integrate from negative infinity up to a constant b, we take the limit as t goes to negative infinity, and then we integrate from t up to that number b. And finally, to integrate from negative infinity to positive infinity, we divide the integral up into two parts, and we integrate from negative infinity up to a, and then from a to infinity. And we can use any number a to break this up. I will say that typically the number that we use for a here is going to be 0. Let's take a look at some examples. So in our first example, we want to determine whether the integral from 1 to infinity of 1 over x dx is convergent or divergent. So we have integral from 1 to infinity. The function is 1 over x with respect to x. By the definition, we are going to take the limit as t goes to infinity, and then we will integrate from 1 to t, the function 1 over x. Now we have the limit as t goes to infinity of, what is the antiderivative of 1 over x? Well, we know it is the natural log of the absolute value of x. And then we will use the fundamental theorem of calculus to evaluate this function at these limits. And so this is going to be the limit as t goes to infinity of the natural log of the absolute value of t minus the natural log of the absolute value of 1. Absolute value of 1 is 1, and the natural log of 1 is 0. And so this becomes the limit as t goes to infinity of the natural log of the absolute value of t can be replaced with just t, because we know t is positive and going to infinity. So what happens here? What is the limit as t goes to infinity of the natural log of t? Well, think about what the natural log graph looks like. We know that as we plug in larger numbers into our natural log function, the values of natural log get larger and larger. Now, they do so very slowly, but this graph does continue to rise indefinitely. And so this is infinity. So because the answer here is infinity, technically that means this limit does not exist, and that means that this integral is divergent. In our next example, we have the integral from negative infinity up to 0 of the function x e to the x. So let's go ahead and use the definition to rewrite this integral as the limit as t goes to negative infinity, integral from t to 0, x e to the x dx. So now we're going to have the limit as t goes to negative infinity of the antiderivative, and then we'll evaluate that from t to 0. But the big question here is, what is the antiderivative? So let's work on that. We have the integral of x e to the x dx. This requires integration by parts. So I will let u equal x, and dv will be e to the x dx. And then applying integration by parts, we get x e to the x minus the integral of e to the x dx. And this is x e to the x minus e to the x. Or I can simply write this as e to the x times x minus 1. So we'll go ahead and put that in here. And now we're going to apply our limits from t up to 0. So this becomes the limit as t goes to negative infinity of e to the 0 times 0 minus 1 minus e to the t times t minus 1. Well, e to the 0 is 1, and this is negative 1, so we have 1 times negative 1, which is negative 1. And then we have minus e to the t times t minus 1. Now I'm going to rewrite this. We're going to say this is the limit as t goes to negative infinity of negative 1 minus t minus 1 over e to the negative t. Now you might be wondering why I'm doing that. Well, it's because when we take limits, we know that typically fractions are better because fractions have a greater chance of giving us a limit that we can use L'Hopital's rule on. So let's think about what happens here. As t goes to negative infinity, the numerator here goes to negative infinity. But as t goes to negative infinity in the denominator, you have e to the negative infinity, which is like e to the infinity. So basically, the top is going to negative infinity and the bottom is going to infinity. So because of this, we can apply L'Hopital's rule to this limit here. Now, of course, don't forget you also have this constant. So we know this is going to be equal to the constant negative 1 minus the limit as t goes to negative infinity of this expression. Now again, we just mentioned this goes to basically negative infinity over infinity. So if I apply L'Hopital's rule, we're going to have the limit as t goes to negative infinity. The derivative of t minus 1 is 1, and the derivative of e to the negative t is negative e to the negative t. And so now what happens as t goes to negative infinity, this is going to infinity, right? So what you have here is 1 divided by negative e to the positive infinity, and this is going to go to 0. So what we have is negative 1 minus 0, which is negative 1. And so this integral converges, and it converges to negative 1. In our next problem, we have the integral from negative infinity to positive infinity of the function 1 over 1 plus x squared. So for this one, what we're going to do is integrate from negative infinity to 0 of our function, and then plus the integral from 0 to infinity of our function. Now we need to do each of these integrals separately. So let's go ahead and work on the first one. If we integrate from negative infinity to 0 of the function 1 over 1 plus x squared, this is defined to be the limit as t goes to negative infinity, integral from t to 0, 1 over 1 plus x squared, dx. All right, so let's go ahead and write down our limit. And now we're going to take the antiderivative of this function. And we should know that this antiderivative is simply inverse tangent of x. And so this becomes the limit as t goes to negative infinity. Using the fundamental theorem of calculus, we have the inverse tangent of 0 minus the inverse tangent of t. Now, inverse tangent of 0 is equal to 0. So we're just going to have negative limit t goes to negative infinity of the inverse tangent of t. And all I did here is I just took this negative and I factored it out of the limit. So what does inverse tangent of t do as t goes to negative infinity? For this, we need to know the inverse tangent graph. And the inverse tangent graph looks something like this. And it has a horizontal asymptote at pi over 2, and it has another horizontal asymptote at negative pi over 2. So if this is the inverse tangent graph, as numbers t go to negative infinity, the graph is approaching this horizontal line at negative pi over 2. So because of that, this is equal to negative pi over 2, which of course is just pi over 2. Now let's go ahead and work on the other integral, this one here. So for that one, we have the integral from 0 to infinity, 1 over 1 plus x squared. This is defined to be the limit as t goes to infinity, integral from 0 to t, 1 over 1 plus x squared. Take the antiderivative, we get the limit as t goes to infinity of the inverse tangent of x. And we're going to evaluate this from 0 to t. So it's very similar to the previous one. We have limit t goes to infinity of the inverse tangent of t minus the inverse tangent of 0. An inverse tangent of 0 is 0. And now we have the limit as t goes to infinity of the inverse tangent function. So as the value of t goes this way, the inverse tangent graph is approaching this horizontal line at pi over 2. So this is just equal to pi over 2. So now, what is the value of our original integral? Well, it's equal to the value of this integral plus the value of this integral. And we just computed that the first integral was pi over 2. The second integral was also pi over 2. And when you add these together, you get pi. This next example is a classical example of improper integration. The question is, for what values of p is the integral here convergent? This is often called the p integral because the function involved is the function 1 over x to the p. Let's divide this up into a couple of different cases. If p is equal to 1, this integral is the integral from 1 to infinity of 1 over x dx. And we actually did this integral just a few moments ago, and we saw that the result was positive infinity, which means that the integral is divergent. So we know that it will not converge for p equals 1. What if p is not 1? If p is not equal to 1, then you have the integral from 1 to infinity of 1 over x to the p dx. By definition, this is the limit as t goes to infinity of the integral from 1 to t. And I'm going to change 1 over x to p, 1 over x to the p as x to the negative p. This will allow us to find the integral more easily. So we have the limit as t goes to infinity. The antiderivative is x to the negative p plus 1 divided by negative p plus 1 from 1 to t. And this is equal to the limit as t goes to infinity. Let's rewrite this a little bit. I'm going to say that this is x to the 1 minus p divided by 1 minus p from 1 to t. Now, 1 minus p in the denominator can be factored out of the whole limit process because it does not depend on t. And then I'm going to plug my upper and lower limits into my function here. And that is going to give me t to the 1 minus p minus 1 to the 1 minus p. Now, 1 to the 1 minus p is just 1. So the question is, what happens to this? Well, it depends on the value of p. So let's just focus in on the limit as t goes to infinity of t to the 1 minus p. Let's think about this. If p is less than 1, then this is going to be a positive number. So if p is less than 1, 1 minus p is going to be a positive number. And this is because you have 1 and you are subtracting a number that is less than 1. Well, that means that this power is going to be a positive number. If this is a positive power, then as t goes to infinity, this is going to be infinity. So this limit is going to be infinity if p is less than 1. What happens if p is greater than 1? Well, if p is greater than 1, then 1 minus p is a negative number because you are subtracting a number bigger than 1 from 1. In this case, we have the limit as t goes to infinity of t to the 1 minus p. Well, what is this equal to? Well, let's think about it. If 1 minus p is a negative number, that means that this power is negative. And what you can do here is you can think of this as the limit as t goes to infinity. And instead of writing t to the 1 minus p, I can do 1 over t to the negative 1 minus p by definition of negative exponents. And this will be the limit as t goes to infinity of 1 over t to the p minus 1. But again, if p is bigger than 1, this exponent now will be positive. And if this exponent is positive, as t goes to infinity, infinity to a positive power is infinity. So you can think of this as being 1 over infinity, which would be 0. So this limit here is equal to 0 if p is greater than 1. So now let's summarize. We already know that if p is equal to 1, the integral is divergent. We figured out that if p is less than 1, the integral is also divergent because it's infinity. So the only values of p for which it converges is when p is bigger than 1. So the answer to the original question is p must be greater than 1 for the p integral to converge. So the conclusion of the work on the previous page is that the integral of 1 over x to the p from 1 to infinity is convergent if p is greater than 1, and divergent if p is less than or equal to 1. We'll want to remember this result for sequences and series later on in the course. Now let's suppose we want to find the area under a curve y equals f of x, where f of x has a vertical asymptote at x equals b. Now we know we can find the area from a up to t as long as the number t is before b. And to do this, we would simply say the area is equal to the integral from a to t f of x dx. But we have a problem at b. At b, the function is undefined. That's why we have an asymptote there. So if I want the total area from a to b, I'm going to have to integrate from a to b f of x dx. But the problem is the function is undefined at the upper limit. And by the way we've defined definite integrals, we know that our function has to be continuous on the interval. Or it might have jump discontinuities, but it cannot have an infinite discontinuity. So the question is, how do we deal with this? Well, we know we can take the area from a up to t for any number t that is less than b. All we need to do is take the limit as t approaches b. So the way we're going to define this is the limit as t approaches b from the left of the integral from a to t f of x dx. And then this integral will exist if the limit exists. And we'll say the interval is convergent in that case. And if the integral does not exist, or if the limit does not exist, then we say that this is divergent. So let's go ahead and give the formal definition, and then we'll do some examples. Next, let's take a look at improper integrals type 2. If your function f of x has a discontinuity at b, and b is the upper limit of integration, then we need to take the limit as t approaches b from the left. If your function is discontinuous at a, and a is the lower limit, then we'll need to take the limit as t approaches a from the right. And if your function has a discontinuity at some number in between a and b, then you will need to divide up that integral at that discontinuity and apply both of these previous definitions. Let's take a look at some examples. So in this integral, we know the function is undefined if x is equal to 2, because if we plug in 2, we will be dividing by 0. So the lower limit is the problem. So how am I going to do this? Well, let's think about it. We're integrating from 2 to 5 of the function 1 over the square root of x minus 2. We know we have to take a limit as t approaches 2, and then we're going to replace 2 here with t. But do we approach 2 from the left or do we approach 2 from the right? You don't have to memorize this. It's actually very simple. If you are a number somewhere in between 2 and 5, so you are somewhere in this interval, if you are approaching 2, you have to be approaching 2 from the right-hand side. Because again, you're not allowed to be outside of this interval because that was the interval on which it was defined. So if you're somewhere inside of this interval, you must be approaching 2 from the right. All right, from there, we just go ahead and integrate like normal, and then we'll take a limit when we're all done. So to integrate this, we're going to rewrite this as x minus 2 to the negative 1/2 power. To do the integration, I'm going to use substitution. When you integrate x minus 2 to the negative 1/2, we're going to let u equal x minus 2, du will be dx, and this becomes the integral of u to the negative 1/2 du. And when you integrate that, you get u to the 1/2 divided by 1/2, which is 2 times the square root of u. So I now know that we're going to be taking the limit as t approaches 2 from the right of 2 times the square root of x minus 2. So don't forget, when you get this answer here, you have to put your x's back in. And then we're going to evaluate this from t to 5. This becomes the limit as t approaches 2 from the right, 2 times the square root of 5 minus 2, minus 2 times the square root of t minus 2. So now we have the limit as t approaches 2 from the right. We've got 2 times the square root of 3 minus 2 times the square root of t minus 2. So the last thing we need to do here is simply evaluate the limit as t approaches 2. But this is a nice continuous function, and if you plug 2 in here, you simply get 0. So this becomes 2 times the square root of 3. And so this integral is convergent. In the next example, we have the integral from 0 to pi over 2 of the function secant of x. So what's the problem with this one? Well, you kind of need to know the secant graph. So if you remember, the secant graph looks something like this, and there is an asymptote here at pi over 2. So when you integrate from 0 to pi over 2, the problem is at pi over 2. So the problem is at the upper limit of integration. So we'll take the limit as t approaches pi over 2. We're going to integrate from 0 to t, the function with respect to x. Now let's go ahead and find the antiderivative. So what is the antiderivative of secant of x? Well, this is one that you need to memorize. It is the natural log of the absolute value of secant of x plus tangent of x. And we're going to evaluate that from 0 to t. And then when finished, we'll take the limit as t approaches pi over 2. So this becomes the natural log of the absolute value of secant of t plus tangent of t minus the natural log of the absolute value of secant of 0 plus tangent of 0. And let's not forget our limit as t goes to pi over 2. So briefly, tangent of 0 is 0, secant of 0 is equal to 1, so this becomes the natural log of 1, and that whole thing is equal to 0. So we just need to evaluate the limit as t goes to pi over 2 of the natural log of secant of t plus tangent of t. Oh, and by the way, I should have mentioned this long ago, sorry, but if we're approaching pi over 2 in this interval, we have to be approaching pi over 2 from the left. Okay, So as we approach pi over 2 from the left, what does secant do? Well, we have a picture right here. As we approach pi over 2, secant is going to infinity. And what is tangent doing as we approach pi over 2? Well, let's remember the tangent graph looks like this. And it also approaches infinity as you approach pi over 2 from the left. So in essence, what this becomes is the natural log of infinity plus infinity, which is the natural log of infinity, which is infinity. And that means that this integral is divergent. In our next example, we have a discontinuity at x equals 1. Now, x equals 1 is not either of the limits, but notice that x equals 1 is between 0 and 3. So when this happens, you have to break it up as the integral from 0 to 1 of your function plus the integral from 1 to 3 of your function. And then we have to work on each of these separately. Now, keep in mind, if either one of these diverges, you can stop the problem and say the whole thing diverges. So let's work on the first integral. The integral from 0 to 1 of the function 1 over x minus 1 is going to be the limit as t approaches 1 from the left of the integral from 0 to t of our function here. The antiderivative of 1 over x minus 1 is the natural log of the absolute value of x minus 1 from 0 to t. This becomes the limit as t goes to 1 from the left of the natural log of t minus 1 in absolute value minus the natural log of 0 minus 1 in absolute value. And this is where the absolute values are really important. 0 minus 1 is negative 1, and the absolute value of negative 1 is 1. And so this is just the natural log of 1, which we know is equal to 0. Now, what happens here? If you approach 1 from the left, as the value of t gets close to 1, the value here is getting close to 0. Now, when you take the absolute value, it means that this is always going to be a positive number. So the number inside here is going to 0, but it's going to be a small positive number as that happens. What is the natural log of a small positive number? Well, think back to your natural log graph. We know that the natural log graph looks something like this. And if we are approaching 0, as we plug in smaller and smaller positive numbers, you can see that the graph of natural log is going to negative infinity. So this is going to go to negative infinity, which means this integral here is divergent. And if this integral is divergent, it means the whole thing is divergent. And that concludes this video lesson.